Okay, hi everyone. This is the last video of the 6th week when we will discuss the exercises that were intended for labs. So we are looking at this script v.pdf. We already take care of the first exercise in last time. So now let's move to the second exercise when we'll be dealing with scale-free models of networks, more precisely the Barabashi-Albert model and the Price model that were both introduced in lectures. So the exercise reads, study the following two algorithms for generating the Barabashi-Albert scale-free networks and Price scale-free networks. And we are given the pseudocode here at the bottom. So let's first think about the Barabashi-Albert model. Let me move to the blackboard. So we have the Barabashi-Albert model denoted G and C, which will generate a network with n nodes, and each new node that when arrives generates C undirected links to the existing nodes. And the links are connected to the existing nodes with the probability proportional to their degree. So node I should be linked to with probability proportional to k sub I. Now, the only thing in this model to think about is that how are we efficiently selecting the nodes proportional to their degree. So how can you easily do that? Next to your graph data structure, you can also store a list of node indices where each node in this list would appear as many times as its degree. So the node I will appear here as many times as its degree. So if we keep this list updated throughout the evolution of the model, every time when we want to select a node proportional to its degree, we can simply select a random element from this list, for instance I, and that I is selected with probability k sub I. And that's all the magic. So let's look at the pseudocode. First I generate an empty queue, which will be this list here, and an empty graph. Then until my graph has n nodes, I add a new node and create links to the existing nodes. And for each link, I simply randomly sample the second endpoint out of this list, which is here denoted by Q, and create a link between nodes I and J. And in order to keep this list updated, I will also on each step add node I to the list and add node J to the list. So the list will, in any time step, contain each node with the as many times as in its degree. So this is regarding the Barabashi-Albert model, which will generate a scale-free network, an undirected scale-free network, where its degree distribution will roughly follow k to the power of -3, which we derived in labs. Now let's also move to the Price model, where we generate a directed graph with parameters n, c, and a. And let's again move to the blackboard. So we are generating a Price model graph with n nodes, where each new node creates C outlinks, C directed links, and we have another parameter A. And where new arriving nodes generates links, it should link to the existing nodes with a probability proportional to its in degree plus this parameter A. So if Q sub A, the same as on the slides, denotes the in degree of node I, the node I should be selected with probability Q sub I plus A. Now again, the only thing to think about is to how to efficiently select the nodes with this probability. And we can use the same idea as we did for the Barabashi model. We simply keep a list of nodes where each node appears in this list as many times as its degree, plus this parameter A. So if I will randomly select a node from this list, I will select it with probability proportional to what we want. The only problem with this reasoning is that so far we are assuming that A is an integer. So that we can actually, let's set A to 2, so that we can actually put two indices I into this list. However, in general, this A will not be an integer, will be a real number, and we would also like to generate networks when we can set this A to whatever positive number. Now, how to do that? It's actually a very, very simple trick. So the exact probability with which node is selected, which was derived in lectures, equals Q plus A, so the in degree plus A, divided by N times C plus A, where N is the current number of nodes, and C is the number of links, outlinks that each node follows. Now, the only thing that we can do efficiently is select the nodes by degree or by in degree, as we did for the Barabashi-Albert model, or we can select the nodes completely at random. So when we select the node with probability proportional to its in degree, we will be selecting the node with probability Q divided by NC. And when we select the nodes proportional simply at random, uniformly at random, each node is selected with same probability, which will be just 1 over n. Now, how can we, with these two simple processes that we can implement efficiently, come up with this to this probability here? It turns out that if I multiply this first probability with C divided by C plus A, which are all just some constants, so this is some number, some fraction, and I multiply the second probability with 1 minus this, so it will be A divided by C plus A, you can compute on your own that these two terms are equivalent. Meaning that on each time step, if we want to link to nodes with this probability, where A is not an integer but any random or any real number, what we do is that with this probability, we should select node proportional to their in degree. And with that probability, with the remaining probability, we simply select the nodes uniformly at random. And the entire process will select the nodes with the probability with which we want. So let's look at the pseudocode. So here it is. Again, I generate an empty queue, which will call my nodes with, and each node will be included as many types as its in degree, not the degree as in the Barabashi-Albert model. And then let's start the network with a graph of C isolated nodes. Then I'm adding one node at a time. Every time when I add new node, I also connect to C existing nodes for C directed links. And with probability C divided by C plus A, I select a node from this Q, which will basically select the nodes proportional to their in degree. And with the remaining probability, I select the nodes uniformly at random. At this time step, we have I nodes, so I simply select one node out of this set here and set it to be my endpoint of the link. And as before, on each step, I am also updating this Q in order to keep the nodes, to keep the indices of the nodes there to be to appear as many times as the in degree of the node. And this is basically it. So what is the main difference between the algorithms? In the first case, in the Barabasi-Albert model, we are generating a scale-free, undirected network with degree exponent 3, whereas in the second case, in the case of the price model, we are generating a directed network where the degree exponent will be that q to the power of 2 minus a divided by c. So the in degree distribution will follow a power law, and we are free to set these two parameters a and c however we want in order to generate networks with different power law exponents. And moving on, what is the time complexity of the algorithms? Obviously, with that kind of implementation, both of the algorithms are simply linear in the number of links, so you can easily generate networks with, say, millions of nodes. Okay, let's move on. Try to implement one of the algorithms or both and generate the scale-free networks corresponding to the larger networks above. We will just do that in general. We will generate a couple of scale-free networks. And what we would also like to do is plot their degree distribution to see whether they really follow a straight line on a doubly logarithmic plot. And we will also compute their degree exponents to see whether the model nicely reproduces what analytical derivations tell us that it should. If we now look at some Java code that generates these two models, let's first look at the code for the price model. So here is the code, and here is the implementation of the price model. What I do, I start with the complete graph on C nodes, and I say that it is a directed. Then I will start this list of nodes that will allow me efficiently sample the nodes proportional to their in degree. This is here called this is here a list called nodes. And what I do to initialize this list, I go through all the edges that were generated above, and I add the second endpoint of the edge to this list, so each node will appear as many times as its in degree. Then I simply generate remaining nodes until I have in total n nodes. On each step I add a new node and create C links out of that node. And for each of these links, I basically select the second endpoint first with probability C divided by C plus A. I select a random element from these list nodes, which will basically select the nodes proportional to their in degree. And with the remaining probability, I select the nodes uniformly at random, which is done here. And then I simply create an edge from my new node I to this selected node, and I also update the list nodes with the second node, so the things will keep updated. And that's all. This will generate a network, a directed network with a scale-free in degree distribution, a power law in degree distribution. Now, see here, I'm setting the number of nodes and this parameter C and A. Usually it's more convenient to, instead of setting C and A, that I set the average degree in the network and the desired gamma exponent of the in degree distribution. And this is done here. So the if I set the average degree in the network to be k, then C is simply 1/2 of that. And if I want a particular gamma, this is the formula that can use, which is basically using that gamma equals this exponent here. Okay, so this is the implementation of the price model. For the Barabasi-Albert model, we could implement the the pseudocode that was given in the lab's handout. However, we showed in lectures that Barabashi-Albert model is just a special case of a price model where we set this third parameter A to C and treat the final generated graph as undirected graph, not directed graph. And this is implemented here. So in order to generate a Barabashi-Albert model with parameters N and C, I generate a price model with parameters NCC and set it to an undirected graph, and that is it. So we only need one implementation to generate both of the models. And here at the top, we are again making a more convenient parameters for generating such a graph, which are the number of nodes and the average degree. And this is basically the only really relevant code here. So if we look at the beginning, what I do is I first generate a price model with parameters k, so the average degree is 16, and gamma 2.5. I print out its properties and also visualize a small variant of this network. So let's look at that. I will not be running the code because it takes more than 15 minutes, and let's not bother with that. So here are the properties of the generated price model. You can see it has 1,000,000 nodes, the average degree is 16, as we said, and also the gamma exponent, or the gamma exponent for the in degree, is around 2.5, so we are happy. Now let's go back to the code. Next, I am also generating the Barabashi-Albert graphs with, again, 1,000,000 nodes and the average degree of 16, and print out its statistics and again visualize the network. So here is the properties of the generated Barabashi-Albert graph. Again, 1,000,000 nodes, average degree 16, and the gamma exponent is close to 3, which it should be according to our analytical computations. Let's look also at the visualizations of the networks. Here is how, just a second. This is how a Barabashi-Albert model would look like. You can see some high degree nodes here shown with green color. Now for the price model, if we set gamma to super low, this will basically generate a star-like graph where more or less everybody connects to 1 or 2 hub nodes. And for larger values of gamma, we get networks that, for instance, resemble the Barabashi-Albert networks, and you again see some high degree nodes here in the middle. Okay, so the last thing that we would like to do is also for different values of gamma. I am here with this function, which is implemented here, generating different graphs with that particular gamma. So obviously I'm using the price model, and for each graph I will be plotting its degree distribution, so to see whether we really get a straight line on a doubly logarithmic plot, and I will also compute the empirical gamma exponent for different values of A and C. So this value here is our theoretical approximation, and how I will compute gamma from a given network, so an empirical approximation of the gamma. I have the code somewhere below here, which is actually quite simple. This is a maximum likelihood estimation of this parameter gamma that you will learn in homework too. So I will not explain it now. Let us just look at the results. So if we look at the log file, here are the theoretical values of gamma, and on the right hand side the empirical approximations. And you can see that in most cases we get values very close to our theoretical estimate. Of course, in order to get even closer, the network would have to be even larger, and we might also have to play with the minimum degree cutoff from which point in the degree distribution we are trying to estimate the power law. However, when values become much larger than 3, where scale-free networks try to basically look very similar like a random graph, the model does not correctly reproduce this gamma exponent as we would, based on the things that we said in lectures, we would actually expect. Now let's also look at the visualization of the degree distributions. So the code generated a MATLAB script that plots these degree distributions. So if we look at them, you can see that we get roughly a straight line for different values of gamma, and larger the gamma, steeper the slope. I mean, I think that it's best, this is best visible here in this part, where you can see the right curve is on the top and the blue curve is on the bottom, and they switch in the tail, and this exactly corresponds to different values of gamma. Okay. So this is regarding this second exercise. Please try to implement these algorithms also on your own and try to reproduce these results. Now we will just orally think about also the third exercise, and I suggest that you look at the printout on your own so that I can move to the blackboard. Okay, what the exercise says is that, maybe we can look that together. The exercise reads, consider different large-scale properties of real-world networks that we have discussed throughout the course. So, networks are sparse, have low average degree, they have single giant connected component, the distances between the nodes are super short, so they usually scale as a logarithm of n. Networks usually have a very high clustering coefficient, much higher than 0, much higher than what you would expect in the random graph. And finally, that they have a power law degree distribution. And the first exercise asks, try to design a synthetic graph model, come up with a graph that generates graphs that are most different from real networks. So we would like to generate a graph that will fail on all of these properties that we have now discussed. And there are many different ways how to do that. Maybe a very simple example would be just to take a path graph. So, for instance, the distances here scale as n, not as logarithm of n, so we have long distances, we fail regarding the distances, so we're happy. Next, the network obviously has no triangles, so clustering coefficient is 0, so we fail there as well. The degree distribution, all the nodes have degree 2, it's almost a regular graph except for the endpoints, so the degree distribution will be nicely peaked and will not follow a power law. Notice that I still have a low average degree of around 2. In order to have, if you want to fail on that as well, we should generate a dense graph. But then if we generate a dense graph, we will probably also have high clustering. So this is kind of, maybe we can think about putting a click here that will make the graph already dense, but still not increase the clustering enough, or something, not increase clustering too much, or something like that. And the last thing is that we do not want to have a single giant connected component like we have now. And how can we correct for that? Instead of having one path, have a couple of paths. So the size of the largest connected component is now around 20%, so we fail on that as well. And at home, you can maybe think about better examples how to fail on all these properties. It turns out that sometimes it's actually harder to generate a graph that will fail on all common properties of real networks than to generate a network or a graph that will actually match all these properties. And this is what the second exercise says. Try to implement a generative graph model that best reproduces the structure of real undirected networks. There are again many different models in the literature that do that. Let me talk about a variation of one model, so-called the copy model, that we also discussed in the lectures. So let's say I already have some graph or some network, and I will have a generative model where each new node arrives and forms some links. And let's say that this new node will first select one node completely at random and generate a link to it, and then it will also randomly select one of the neighbors of this node and create the link to the neighbor. So this link here. Now, what are the properties of such a network? We have shown in lectures that because of this second link, when you link to the neighbor of a randomly selected node, you are also to some extent, the probability of linking to a node is roughly proportional to the degree of the node, so we will be generating a scale-free network, a network with a power-law degree distribution. So we are happy about that. Next, since you connect to the node and to its neighbor, every time you create a triangle, and I can also connect to a few of the neighbors, and I will be creating a couple of triangles, so that kind of network model will also generate a graph with high clustering coefficient. So we have that as well. Now going back, distances. Since we have a scale-free graph, we have shown many times that, not shown actually, just said, but it's derived in your course books, that scale-free networks are ultra small walled, they have short distances, so we also get a graph with short distances. And finally, obviously, we get one large connected component, and the average degree of the nodes is small, as long as these new nodes forms just some constant number of links that does not scale with n, so we also generate a sparse graph. So we basically reproduce all the properties of real networks. Okay, so this is this second part, and the third part, or the third question, is that it asks, does your model have a reasonable interpretation or explanation? In effect, it does. Okay, let this be a friendship network. So this is me. I come to some society. I randomly meet some person and become its friends. And after a time, he will also introduce me to his friends. So I will become friends with friends of the friends, and so on. So to some extent, the model can be a reasonable approximation of a social network. Does the model also reproduce the structure of real directed networks? So think about that all these links that I'm forming are directed links, and in fact it does. For instance, think about citation networks. So I write a new scientific paper, I cite a paper that started my research or triggered the thinking about this problem and so on. And then in this paper, I also learn about some other papers that this first paper cites, and I maybe discover that these are also relevant to my research, so I also link to them. So basically, I copy the citations of the first paper. So in that case, it will generate a directed network with an in-degree, where in-degree distribution will follow happy again. And And again, at home, you can think about other reasonable generative models that would reproduce properties of real networks, and in the literature there are really many. So this is basically it for this video. Thank you for listening.